The Microwave Landing System, MLS, was designed to replace the ILS with an advanced precision approach system that would overcome the disadvantages of the ILS and provide greater flexibility for its users. In 2009, London Heathrow was the only civil airport using the system. Advances in another landing system, the Local Area Augmentation GPS system, may, however, influence the decision of other airports, especially in the USA, as to whether or not to introduce MLS. The universally installed ILS has several disadvantages. These are: there are only 40 channels available worldwide. The azimuth and glide slope beams are fixed and narrow. As a result, aircraft have to be sequenced and adequately separated, which causes long delays. There are no special procedures available for slower aircraft and short takeoff and landing aircraft. ILS cannot be sighted in hilly areas, and it requires large expanses of flat, cleared land to minimize interference with the localizer and glide slope beams. Vehicles, taxiing aircraft, low-flying aircraft and buildings have to be kept well away from the transmission sites to minimize beam bending. It suffers from FM broadcast interference. The MLS has the following advantages over the ILS. It is not subject to sighting problems, and because of its small size, can be sighted on the taxiway side of the runway. It operates in the SHF band, and so is not affected by ILS or FM transmissions. 200 channels are available, 5 times the number available for ILS. It is available to light aircraft, helicopters, and short takeoff and landing aircraft. Further advantages are that aircraft can choose various approach routes. Landing delays in poor weather are reduced. Installation costs are much lower. It has a built-in DME. Equipment failure is indicated by flags. Flare and back azimuth functions are possible, but not currently implemented. The azimuth coverage is much greater than conventional ILS. It is 40 degrees either side of the runway QDM, and it extends out to between 20 to 30 nautical miles, and up to a height of 20,000 feet. The elevation transmission provides a wide range of glide slope angles, from 0.9 degrees up to 20 degrees. And as the elevation signal extends through the whole of the azimuth coverage, it provides precision glide slope guidance at all points where azimuth guidance is available. Aircraft are therefore able to make an offset approach. That is, they can join the approach procedure as close as 2 nautical miles from the airfield. This allows greater traffic flow, quicker approaches, and may improve noise abatement. A secondary system is provided to give go-around and departure guidance up to 20 degrees either side of the runway direction, up to 15 degrees in elevation, to a height of 10,000 feet and with a range of 10 nautical miles. An additional advantage of MLS is the ability of the system to transmit auxiliary data such as station identification, which always starts with M for MLS, system condition, runway conditions, wind shear and weather. The ground components define a coordinate system in space, and the aircraft's position in this reference frame is fixed by airborne equipment. The 3 space coordinates are azimuth angle, elevation angle, and distance from a reference point on the airport, and they are generated by separate subsystems. The forward azimuth subsystem is located beyond the runway stop end, on the extended centerline and radiating in the approach direction. It defines azimuth position. The elevation subsystem, located to one side of the runway and also radiating in the approach direction, defines the elevation angle. A DME beacon is co-located with the azimuth element, and it supplies slant angle distance from that point. The range of these systems is approximately 30 nautical miles. A missed approach azimuth subsystem, located ahead of the runway threshold and radiating towards the stop end, provides guidance for missed approach maneuvers. A flare subsystem near the elevation element is designed into MLS, but ICAO have stated that it is not intended to be implemented. The airborne equipment is designed to continuously display the position of the aircraft in relation to the pre-selected course and glide path, along with distance information during approach as well as during departure. Aircraft fitted with MLS equipment, such as Airbus, will display the information on their electronic navigation screen. The display is similar in principle to the ILS, in that it shows if the aircraft is too high or low. However, it is different from the ILS in that the indications of right or left are given relative to the selected course. So here, for instance, we initially get a command to follow the offset course until we are in line with it. The indication we see here is turn left, because the runway is left of the aircraft's course. The receiver control unit looks like this. Alternatively, in order to receive ILS, MLS and GPS transmissions, aircraft are equipped with multi-mode receivers and a combined control unit for ease of use by the flight crew. The system is very accurate, giving a minimum 95% lateral accuracy of no more than 20 feet either side of the centerline at the approach reference datum, which is 50 feet above the threshold at the centerline. ICAO recommend an accuracy of 13.5 feet. Degradation can be no more than twice this figure at 20 nautical miles, the coverage limit. The vertical accuracy at the same datum is plus or minus 2 feet, and at 20 miles degradation must be no more than 0.2 of a degree on a 3-degree glide slope. MLS employs the principle of time division multiplexing, whereby only one frequency is used on a channel, but the transmissions from the various angle and data ground equipments are synchronized to assure interference-free operations on the common radio frequency. Azimuth and glide slope location are both achieved in the same way, by the use of time-referenced scanning beams. The azimuth beam starts its two-sweep at one extremity of its total scan and travels at a uniform speed to the other extremity at a scan rate of 13.5 scans per second. It then starts its fro scan back to its start position. The time interval between the reception of the to and fro pulses is proportional to the angular position of the aircraft in relation to the runway on course line. So, the maximum time interval between the passage of the to and fro beams would be measured when the aircraft is at the extreme left of the coverage, and minimum time when the aircraft is at the extreme right-hand edge of coverage. The same principle is used for the elevation calculation, but the scan rate is 40.5 scans per second. The distance of the aircraft from the threshold is provided by DME. For Cat 2 and Cat 3 approaches, a precision DME DMEP, accurate to within 100 feet must be available. The number of channels available for MLS is 200, spaced 300 kHz apart, from 5031.0 MHz to 5090.7 MHz in the super high frequency band. The wavelength is about 6 centimeters. Since the basic technique is that of time multiplexing, all functions can take place on a single channel. Essentially, each function in the time-space transmission is a separate entity and is preceded by identification preamble. The receiver can therefore recognize each element of the sequential transmission. The emission designators for MLS are N0X, the unmodulated carrier, and G1D, the data transmission component. These are the main points to remember. The basic principle is a time-referenced scanning beam. The frequencies used are 5031.0 MHz to 5090.7 MHz in the super high frequency band. The four elements are the approach azimuth with DME, the elevation, the back azimuth, and the flare. The approach azimuth coverage is plus or minus 40 degrees, out to 20 nautical miles. The elevation coverage is up to 20 degrees, up to 20,000 feet. The back azimuth coverage is plus or minus 15 degrees in azimuth, out to 10 nautical miles, and up to 15 degrees elevation, up to 10,000 feet. The primary advantages are a flexible approach direction, a flexible glide path angle, no sighting problems, and no FM interference. This concludes the lesson on MLS.